So let's start simple. A dot B cross C, is it equal to A cross B dot C? So what do we do? What's the first step? Assign the index. So this is a dot product between a vector and another vector. So we'll assign I for simplicity, or you can assign whatever you want. I to this entire thing, right? And since it's in bracket, we'll treat it as a vector for now. So we'll write it AI, that bracket I. In this bracket, it should lead with the I index. So I should write, so I should assign some vectors here. So I'll assign J and I'll assign K. So it becomes epsilon IJK BJ CK. Yes. Now I want to go here. I want to do some sort of dot product with C. Currently it's a dot product with A. So you know that some shifting has to be done. C has an index of K. Either you change this part, or you change I to K or K to I. So let's do that, because ultimately we want some sort of, so you need to have a direction where you want to take your derivation, right? Some sort of I, or some sort of K or K. So CK is already there. So let me just take this outside, because I can do shuffling here. There is no derivative, and in Einstein notation this order doesn't matter. So let's do step by step. AI BJ CK. Now I'll shift. I'll make one change. Minus epsilon KJI AI BJ CK. I'll keep this as it is. If I make change here also, then I have to make it plus. All of you are with me? Right? All of this was in the videos. Right? Now we have the perfect ingredient, right? It looks somewhat. Sine ki we'll do tension later. So you have C here and then this here. So just for simplicity, let me put a bracket so that it somewhat resembles this. Does it resemble? So you can either do two things. Either you can write it in the vector form back, because you had to write it in the Gibbs notation back. So what is this? Epsilon KJI A B. A cross B or B cross A? This is a common mistake. This is A KJI and this is BJAI or AI BJ. Right? So you can be cautious of it and write this is B cross A, and then this whole has index C and this has index C. But this may be, you can do mistakes here. So what you can do, I advise, is whatever you see here, just make this order back again IJ. Na? So make this epsilon K IJ. So I'll flip this part so that it forms nicely AI BJ CK. Now you see this A cross B has a whole index of K dotted with K. This has index of K. Yes? Any questions? Now is the time, because then I'll ask the question and then you'll lose marks if you have doubt. Okay. हाँ, कोई फर्क नहीं पड़ेगा, बिकॉज ये क्या है, स्केलर है वेक्टर है, दोनों साइड स्केलर ही है ना, तो फर्क नहीं पड़ेगा. अगर एक साइड आई होता दूसरी साइड के करते तो हम ऐसे करते कि दोनों साइड इंडेक्स आई आई हो. वेक्टर हो तब वी हैव टू बी सेंसिटिव. वी डिड वन एग्जांपल इन द वीडियो आल्सो, राइट? हाँ. Okay, let's do another example. The gradient of alpha into f, where alpha and f are both scalar fields, meaning they are functions in space, they vary in space. So here alpha is a function, I mean, it's a function of x, y, and z. In books, it will be written as alpha as a function of r vector. Yes? Both the same thing, position vector. Similarly, f is a function of some position in space. What will you do? Simple chain rule. It's just that it's a chain rule with an index. So you'll assign an index here. Dou by dou xi, you can assign whatever you want, into alpha into f. Simply, it's dou alpha by dou xi, and f is out, plus. Again, write back in Gibbs notation you get. Yes? It's nothing different than dy dx of alpha into f. It's just that we have done it in 3 directions. Okay. Now, let's do another one. By the way, you could, one thing to note here, I was taking this out and doing that business, right? Resist the temptation of taking this out, right? Whenever you have vector operations with this guy, you have to respect whatever is in the brackets. You can shift them around for your convenience, but don't take them outside the derivative. Okay. Question, another one. Divergence of alpha gradient of this. So what is this going to be? This is a vector dot product with another vector. This is going to be a scalar. So whatever we assign, we have to assign all the underline tildes. So we'll assign I and I, right? So what can we write? Dou by dou xi alpha dou f by dou xi. Simple as that. Now we can take this inside. Again, apply the chain rule. Dou alpha by dou xi plus, dou f by dou xi plus, is this clear? This is the first part. You do derivative with respect to this, leave this alone. Same chain rule that you have seen before. I mean, if you are like scared of this I, just imagine it's not there. Imagine I is not there and you're just doing a simple derivative. So it's class 11th, 12th stuff, right? What will happen to now the second term? It will be alpha dou square f by dou xi or dou xi square. Once you do this, apply I again in your mind to not be afraid of it. So this is dou alpha by dou xi is, but this has an index of I, this has an index of I, so it's a dot product, because in the end, remember, it's a scalar. Plus alpha del square f. Easy? Let's make it a bit tougher. Divergence of curl of vector. Del dot del cross v. What it should be? It should be 0, because what is curl of vector? The amount of circulation. So if there is a field which is rotating any small circular element, it will have some axis, but that axis, if you take the divergence of that field, resultant field, that will be 0, because there is no net in or out. So assigning index, by the way, what is it? Vector or scalar? Scalar, right? So assign I, dou by dou xi, the entire thing should have an index I, but what will we write now? Now you have to tell me. See, the overall index should be I. This is like a cross product. So if you're scared of this opposite triangle, just imagine it's some vector. So what will be right? Epsilon j I j k. Okay, so we are assigning j and k. Dou vk by dou xj, or dou by dou xj into vk. Okay, now we have to expand it to see if it's indeed coming 0 or not. Right, it should come to 0. Can we take this out now? I told you that you have to respect the boundaries here, but can we take this out? Why not? Derivative, but this guy is not a function of space. This is just, it just has values +1, -1, 0. Right? So it's purely a logical parameter. If given the combination of ijk, it will give you the number. So you can take this out. Epsilon ijk, and take this inside. So you have dou square vk, dou xi, dou xj, dou xi, dou xj. Yes? Now we'll use two rules of one rule of vector calculus, we'll use one rule of differential calculus, and then we'll say contradicting each other, therefore 0. What is it? So we'll do two things. One rule of Levi-Civita we will use, Levi-Civita or vector product rule, and we'll say we are going to switch this. So as I said, you can either switch this or switch this. You switch this, so you apply a minus sign and write a minus epsilon ijk dou square vk by dou xj dou xi, and you switch this using the mixed derivative property, because the order of this doesn't matter. So you can make this j and make this I. What you'll get is plus the same thing here. A quantity is equal to its negative, meaning it's 0. Okay. Now, should we do one more example before I give you the questions? One last. Curl of alpha into vector. Alpha is a function of space. So what is this going to be? Vector or scalar? The entire thing? A vector, right? So let that be I, the entire thing. So we'll assign the entire stuff as I, and so then the internal constituents must be given an index. So what should we give this? J, and let's give this k. K means this is k. So what should I write? Epsilon ijk, then this is this j or del by del x. Alpha vk. Yes? Correct, right? Now what are we proving? What is this equal to? So it will come as a product of two things, because this has to be applied as chain rule. So you can write epsilon ijk dou alpha by dou xj vk plus alpha dou vk by or dou by dou xj of vk. Yes? What is this and what is this? There is also, I mean, not just writing a Gibbs notation into answer notation is a practice, but you have also to practice how to come back to the compact Gibbs form. So what is this and what is this? So this is epsilon ijk dou by dou xj, whatever, some gradient, some vector into another vector. So isn't it like epsilon I j k, some vector with an index j and some vector with an index k? So it's this cross with this. So what should I write? Curl of, del of alpha, that is a vector, cross with v. Yes or no? Plus, what is this now? Epsilon ijk into alpha. Alpha is fine. I mean, you can just take it outside also. Doesn't matter. So epsilon ijk, dou by dou xj of vk. So this is epsilon. Come on, yeah. Del cross v. So this is your answer. Yep. Okay. See, as soon as you start to get overwhelmed with the notation, at first it may seem too much. For some, it may seem, what's the big deal? It's fine. Everybody has their own frequency of learning. But if it seems difficult, just treat these dels and dou by dou xj's वगैरह as a vector. Okay. And when you are coming back from a complex Einstein notation or a lengthy Einstein notation to a Gibbs notation back, again, try to see them as, okay, this is nothing but a vector with an index j, vector with an index k. That will help you.
So in the last step, we can take out the alpha there, outside optional.
We can, I mean, for this, just for this.
So first,
This one? This is dou alpha by dou xj. Na? We can't. Only for that term we could take out. That's why it's out. Okay. So let's do them quickly so that you know whether you were. How many of you got false? No one got false. For any question. Both are true, na? But okay, I mean, the approach will be seen. So both are true, na? Let's see. Oh, some people are not. Anyway, it doesn't matter what you write. The derivation matters. Okay. ठीक है? Please बैठ जाओ. अभी और करेक्ट नहीं करना है. बैठ. Okay. So let's see question number 1. Divergence. Should I do it or leave it? So this is from assignment. So those who have solved assignment question will be benefited. This we did in the class today. It's just that this was a vector. So those who paid attention will benefit. Either of ways, if you are sincere, will benefit. Anyways. V cross W, fine. This is a vector or scalar? Scalar. So index I assigned, dou by dou xi. This is epsilon I j k, V j W k. Okay, this can be taken out. Epsilon I j k, dou by dou xi, V j W k. You can apply the chain rule here and write it as dou V j by dou xi W k plus V j dou V W by dou xi. Is it correct or not? Now, what you have to do is just look at the two constituents. Epsilon I j k. This is k, this is I j k. So you can shift it. What can you write? Minus epsilon k I j W k. Yeah. Oh, sorry, k I j. Na? Good. I shifted twice. Na? I first made it k j I and then k I j. Then what I get? This dotted with. This is W dotted with epsilon k I j curl of V. Exactly like the first problem we did today. Okay, let's look at this guy. Epsilon I j k Vj dou by dou xi of wk. What do we need to see if this is correct? V dot, right? So do one switch. J I Vj into the extra stuff, so minus Vj into epsilon J I k dou by dou xi wk. So it is V dotted with curl of w. That's correct. Second derivation. Curl of V. Right, so this is going to be vector or vector, right? Cross product only. So what, the entire thing is I, this is J, this is K. So epsilon I J K dou by dou x J, this thing K. This thing has to be K, so what do we have? Epsilon K L M dou by dou, this one, XL, right? V M. This can be taken out without any harm. Epsilon ijk, epsilon KLM. I can shift these two, so two changes. So make it with the plus sign only. LMK KLM. So let me make it minus MLK. Maybe another one. LM. Two changes, right? Dou by dou xj dou by dou xl into Vm. Oh, sorry, operated on Vm, not into, right? Because these are derivatives. Now, what will I do? Apply that. I don't even need to see that. I can just do simple one. This guy, this guy. So what I have? Epsilon IL epsilon JM minus the other one IM JL whatever dou by dou. What I meant, I don't need to see here. I still need to see here. Okay. Now you can apply this to this once and then this to this once. Let's see. What do we have? Okay. This index, what did we decide to be? This whole index. Sorry, this whole index was I, right? So whenever we are substituting, we have to make sure keep it I. So L, let's make Li, and let's make Mj. Let's make Mi, let's make Lj. We decided to do that. So dou by dou xj, okay, let it be. Dou by dou xl, L in this case would be I, into Vm, M is J, minus M should be I. Okay, so I'll let it be dou by dou xj, let it be. L should be J, dou by dou xj. So it is flipped, na? I. M is I, M is I. Now we have to go back to Gibbs form and see if it's true or false. Now what is this? Let's go the easy one. Dou by dou xj, dou by dou xj vi. Repeated index, sum kar do. This is nothing but Laplacian. Laplacian of a vector vi. So this is del square of v. What is this? J dou by dou xj. So I can shift it using mixed derivative property. can bring this here. So this is dou by dou xi of dou vj by dou xj. What is that? Dou vj by dou xj. Dot product between this derivative and this. So divergence of vector. So we get dou by dou xi into divergence of vector. Yes? Meaning gradient of this scalar, which is a divergence of vector, minus, that's minus sign is there. So both are true. Okay. So this is fine. How we got this? Now I have this. Now I want to now I have these indices. These are Kronecker deltas. They instruct that in within the expression. अभी ये दो expressions हैं. In this, L has to be equal to I, or I is to be equal to L. We know that left hand side is a I index. Let's operate with that rule. So L has to be equal to I. So wherever you see L, make it I. Wherever you see M, make it J. That is one item. So second item, you do the ulta. Wherever you have M, you make I. Wherever you have L, you make J. That's what we did. So here, we have dou by dou xj. We decided not to touch because things will be replaced into I and J. So whatever is I and J, let it be. M and L ko we will substitute. So dou by dou xl. In the first item, L should have been I. So I just changed that. This item, Vm. M according to this rule was J. I made it J. Same way, I approached this, but I kept this constant. But this was flipped because this was flipped. Yes? Where? This? Where? This part? Should I explain again? So you are okay with dou by dou xj, dou by dou xi vj, right? Now what is your question? If I am flipping this, there is no epsilon, na? There is no Levi-Civita tensor. We made it Kronecker delta using the identity. Only if you are making sign changes when this guy is around, only then. Now it's just some simple vector product. Fine. So I mean, the point is to make mistakes. Now that I've seen so many of you have done mistakes but attempted, honestly, this is 0.5 marks. Okay. But some marks to reward you. So you basically practice, okay? And we'll start with heat and mass. So first I'll take you from heat transfer, but from heat to temperature. How do we go from heat to temperature? So imagine there is a cup of water on this table. You start heating it. Okay, start giving it some. What will happen to the system? The molecules. So some are saying sensible heat, some are saying latent heat. So we know very well now that heat is of two kinds, or heat change is of two kinds: sensible and latent. Why do we call it sensible? Because we can see the change in temperature, right? Why do we call it latent? No, but what is the meaning of latent? Hidden, right? Meaning that when phase change, the temperature doesn't change, but the heat is released or consumed. So sensible heat is associated with temperature change, associated with phase change. We'll mostly look at in this course the sensible heat aspect. And if I take the sensible heat idea forward, so can I just say that the change in heat is proportional to change in temperature in some sense? Yes? But is that all? If I have 2 cups of water, one is I added polymers in it or some glucose in it, another is just pure water. I heat them up, I provide the same amount of heat. Will they rise the same amount in delta T? Why? Different conductivity. Mein. Heat capacity. So the heat capacity connected to two very different things, right? So different materials have different capacity to store heat. Yes. So, in other words, I mean, if you take, I mean, as the definition of heat capacity goes, or specific heat capacity goes, that if you want to heat water of 1 gram from 14.5 to 15.5 degrees Celsius, how much heat is released or how much heat is taken by that sample of water? 1 calorie in joule, it is kilojoule per kg Kelvin. Yes. So that's the specific heat capacity. So meaning that is proportional to this. This is a proportionality to some Cp, and this proportionality to mass. So this is your specific heat capacity. Heat capacity would be mCp. The units are joule per kg Kelvin, not kilojoule. So 4200 something joule per kg Kelvin. Okay. Why different materials have different capacity to store heat or release heat? What does it mean? Degrees of freedom is a थोड़ा अच्छे से बताओ. For example, what do you mean by degrees of freedom?
Cross-linked polymer has lesser degrees of freedom than a non-cross-linked polymer with random arrangement of molecules. So one can absorb more heat.
So by degrees of freedom you mean configurations? Okay. Or someone said simply intermolecular structure, lattice structure, right? Which material has the most practical and most highest heat capacity? Huh? What? Diamond. We are not on conductivity yet. Water, right? Water has one of the highest heat capacities. Why? Yeah, but why? Because of whatever you said, degrees of freedom and interactions. Because of hydrogen bonds. And the water is mobile. So you heat it up, it jiggles, they break, they go somewhere in the colder area, they make bond again. So it's very sturdy, it can store a lot of heat. Right? So that's one of the reasons why it's used in chemical engineering industry a lot as a heat storage material. You have some heat coming out of your reactor, fine, put some water, store it there. It will store a nice amount of heat at a lower temperature. Instead, if you didn't have water, if you use something fancy for the sake of using it, it will cause you higher temperature for the same amount of heat. And that's disadvantageous because now you have to insulate that very high temperature. So it's nice not to store so much amount of heat at relatively low temperature, right? Because of its high capacity to store heat. Okay. So with this one can write Q is equal to T capacity to store or release heat per delta T multiplied by delta T. Yes, that would give you the heat. And this capacity I mean joule per Kelvin. So the MCP. Now let's come to the diamond part. Experiments have revealed or have, let's say you do some experiment and you realize that the spread of this heat, so let's say from experimental observation, you say that spread of the heat depends on material, and that's not really related to the capacity to store heat. So let's say you did some experiments, and this you found that the if you keep two materials at different temperatures, and bring them closer, there is a transfer of heat. By the way, before I say that, if these two materials at the same temperature, can they have different capacity heat stored within them? So there is a heat, some sense heat difference between them, the amount of heat that they contain. Will there be heat transfer? Both are the same temperature. So temperature is something that governs the spread of heat. Now, and once you realize that, you do some more experiments, let's say hypothetically, and then you say the statement out of your lab, spread of the heat depends on the material, but that property is given by, let's say, thermal conductivity. Let's say your Fourier. Okay, for same delta T, K material. What is the unit of thermal conductivity? Watt to meter Kelvin. We'll discuss more in detail about Fourier in a moment. But just let's say that the spread of heat depends on K, and you all know this from Fourier's law. Q is equal to minus Ka dt by dx. But what would you say to this? Spread of temperature depends on, is heat the same thing as temperature? We just did a discussion, right? Different materials have different capacity to store heat. So as you are doing this experiment and let's say maintaining this at higher temperature, maintaining this, let's say one material only, high temperature, low temperature, heat is spreading. So spread of heat is different than spread of temperature. That should depend on what? Somewhat on K, but some other parameters should also come. Don't speak from memory, just think about the concept. Area. Not really, I mean, not really area. I'm talking about the material property, which is intensive, not dependent on how much material you took, what is the area you took. Coefficient of thermal expansion is just for fluids, how much density expanding. I'm not talking about that. I'm talking about, let's say, solids, simple solids. So this K determines spread of heat. Okay, let's go back here. Q was the heat content, or if you change the heat delta Q, if you divided it by mCp, it gave you change in temperature. So the spread of heat must be divided by something. Yes or no? So the heat, in other words, come to it physically, heat is spreading. As heat is spreading, the temperature is rising according to how much it has the capacity to store or release heat. So it should have some element of, it should depend on Cp also. If Cp is really high, means it can store a lot of heat. Will the temperature spread? No, right? Whatever heat came, it will just eat it up. So, can you imagine that it should be somewhat like this? But units don't match. Rho Cp, this gives you alpha. What does rho Cp now mean? It must mean something. So it is the rate of spreading of heat divided by the volumetric heat capacity. So it is mCp by V. Heat capacity per unit volume, because temperature is spreading volumetrically, right? Yes or no? Again, there is another way of arriving at the spread of temperature. In many of the textbooks, when this Fourier's equation is written, people describe what is thermal diffusivity. You can also go and check. Typical, at least UG books have this, and they write alpha determines the rate of spread of heat. That's not really true. More specifically, it's talking about rate of spread of temperature. Yes. Okay. Okay. So now this is the general discussion of heat. Let's go for mass transfer and how we go from mass to concentration. And for this particular discussion, I have some chemical in mind. I have a jar of water and I'm inserting another chemical in it, and I'm observing this mass to concentration idea. So, speaking from chemical point of view, mass of something you might want to write in terms of molecules. Yes, because ultimately, you know, molecules is all that is the reality. So, if you want to say what is the mass of this, let's say it's made of any material, diamond, water, gold, whatever you want to say, what would you write? Number of into number of molecules into molecular mass. But there is another definition nowadays we write. We don't really write number of molecules, right? Because of one guy named as Avogadro. So what do we write? Number of moles into the molecular weight, na? So number of moles, and this is usually in gram per mole. If you had some, if Avogadro was not there and all that development didn't happen, what would you have? The unit for molecular mass. If you're not operating in gram per mole, gram per molecule, na? Then you would have in that alternate universe, then you would have water. What is the molecule? What is the mass of one water molecule? You do that in electromagnetism, electrostatics, na? What is the mass of one electron? 10 to the minus something. But you don't have some condensed version, right? Some exponent. Yahan pe we have 10 to the power 23 taking care of us. So we can write gram per mole. Water has what? 54 point something, right? 54.55. 18 point something. 18 point something. Yeah. 16 plus 2. Okay. All right. I tend to sort of see these analogously, since we are doing transport phenomena, some analogy you have to make. So I try to make it. But now consider this example. You have 10 grams of pure sugar syrup and another case 10 grams of pure brine salt, NaCl. Which one will pack more constituents? If you have a jar and in that you put sand, how many sand particles will be there? Lots of. You remove the sand, put lots of marbles. Kids used to play in my time in childhood. Less marbles will be there compared to sand. So same mass, but they are made of different constituents. Yes, and why do and those constituents are basically molecules. How many number of molecules there? So how many molecules? Sugar is usually made of sucrose. It's a long polymer, I'm sorry, because of you I'm saying polymer. It's a long chain molecule. NaCl is small, so it will have more constituents, more molecules per 10 grams. Yes. Why do I focus on molecules? Because or why do chemical engineers or basic chemistry, or whenever we talk about mass transfer, we care about molecules? Because molecules, एक तो diffusion, because the more number of molecules are there, the more propensity they will have to spread. Second point, the smaller they are, the higher diffusion coefficient they'll have. You must have noticed this in mass transfer. Smaller molecules jiggle a lot, diffuse a lot. Another incentive to use molecules instead of mass. So I'm trying to build a case why mass is not used. Why don't we say ki this syrup, what is the concentration in this? We say no, it's this many molars or mole per liter. We don't say really gram per liter. In chemical reaction, for example, the stoichiometry is intimately related to how many moles are there, how many molecules are there, not what is the mass of that compound. Okay, so there is a rationale to use molar concentration. So if you were to do mass concentrations, typical definitions that you have in your transport book is sugar, salt. This is your mass fraction, 10 grams in 1 liter solution, let's say. Both sugar and salt, if you go by this notation, then both will have the same fraction. But it's not really good, right? You know that this has more constituents, so you need to use different way of looking at it. So we use molar concentration instead of mass concentration, and we say concentration of sugar is 10 grams by 1 liter, but divided by the molecular weight of sugar, sucrose, whatever that is, that comes out to be roughly 0.03. The calculation is not the point, I'm just writing mole per liter. If you were to do this for salt, again 10 by whatever, you will get 0.17 mole per liter. So you see that you have captured the constituents better here. This sort of description was just saying same hai, right? Similarly, there is a definition called mole fraction is independent concentration by total concentration. This is sum of Ci. Okay, pretty basic stuff. What we covered here about spread of heat and spread of temperature, can we say something about spread of concentration in mass transfer? Spread of concentration is governed by diffusion coefficient. The units of alpha are same as meter square per second, same as the diffusion coefficient. So please write, I don't have space to write, please write the spread of, if you're taking notes, considering any example of sugar or salt, the spread of concentration depends on the diffusion coefficient of salt or sugar. And in this course, we will be taking dilute solutions, binary mixtures, because at least in the starting part, because when you have multi-component mixtures, the diffusion coefficient is not so simple to write. Concentration differences of one kind can induce fluxes of other kinds. Okay, but for now, if there is a salt concentration, salt flux will be there, and Fick's law. So these laws these are also known as constitutive laws. These are based on, or you can also call them empirical laws, meaning derived from experimental observations for simple materials. Exotic materials will not obey these simple Fourier's and Fick's law. And these laws are for static or quiescent media. So in the first part of the course, I'm not going to assume any fluid flow because I just want to work with equations and governing equations and whatnot for quiescent medium. So simple diffusive heat and mass transfer we will look at. So let's write the Fourier's law. If you have a slab and you conduct this experiment, let's say you are Fourier conducting experiment, you apply temperature difference here in one experiment, temperature difference here in one experiment, temperature difference here in one experiment. So you have three areas, you have three directions. In each of these directions you can write the Fourier's law. So if I write in terms of flux, it will be minus K dt by dx, but I should be careful. Each direction I am doing this experiment. So let me write K Qx dou t by dou x. Should I write it Kx for now? I didn't say what kind of material it is. So let me just write Kx for now. Can I write Qy is equal to minus Ky dou t dt by dy? Q dot z is equal to minus kz dt by dz. All of you are now experts in vector calculus. Can we write it in the Gibbs notation, compact form? Q vector is equal to, Q dot vector is equal to something into gradient of temperature. It is not easy, you have to think of it. This has what index it has, whatever index it has, I, it has the same index. So this and this should be same index. So what should be here? K vector. If you do K vector, then what will happen? ये तो स्केलर हो जाएगा, तो गड़बड़ हो जाएगी. क्या करेंगे? Matrix? Tensor? We don't say matrix here. We are high-fi people. Tensor, right? So if I write this, let me minus sign because there's minus sign. What? If you are accepting and shaking your head, then you have to tell me what is this K. What should be the K so that this is true in the expanded form? Kx here 0 0 yes, this is your fixed law in 3 dimensions. Similarly you can write, sorry, this is a Fourier. Similarly you can write fixed law, right? Now I did not say that these kx, ky, kz are equal. If they are equal, then you can just write q dot is equal to minus k grad t. So k then becomes a, k comes out because k is same, and then it is just I, identity matrix वगैरह same. Clear? Should I repeat? Huh? So this K tensor is there. Kx, ky, kz I have assumed to be general, not equal. If they are equal in a special case, meaning if this material is like an amorphous material or a pure metal or a homogeneous material, but an important label here, thanks for asking again, I forgot this almost. If the material is isotropic, meaning wherever you have heat transfer, it's same in all the directions. And you can imagine this for a slab of gold. Even this duster, this is not made of real wood, this is made of engineering wood, meaning wood has been shredded and binded together. So you do heat flux wherever, you will get the same. If you cut a bark from tree and make a duster out of it or make a wood out of it and do heat transfer through it, K will not be same. Why? To see that, go to resources section. And the faster you do it, the faster I'll leave you. So I'm giving you an example of anisotropic materials. Okay. Where K's are different in each directions, and see for yourself how does that material look like. Have you observed, have you seen chopped wood fresh from tree? It has these grains. So those grains are actually air pockets. So do you see the, so in the resources section, what is the name of the file? Some anisotropic something. Yeah, just click on that, it's a PDF and the first page of the PDF. Can someone show me? It's opening, is it? Yeah, so see the first image, the brown image, yeah? You can see it, right? So one is the top view and the another is the microstructure view, the view inside the constituent or the geometry of it. Huh? So you can see that heat transfer through one direction will be nice because it's going through wood. In the direction where there are air pockets, it will be difficult. Yes or no? So either one, so if it is the Z direction or the third direction will be facing a lot of air pockets. So then this will be smaller, these two will be roughly equal. Clear? Yes or no? Similarly, graphite has this property. If you're doing research on graphite, let's say, it will have anisotropic conductivity. You know in class 11th, 12th, you know the structure of graphite? There is this sheet-like structure and then there is gap between them and there are on the sheet. So the electrical conductivity as well, I mean, you can also write Ohm's law for this, anisotropic Ohm's law. The conductivity along this direction is very fast versus the perpendicular. Heat transfer along this direction very fast compared to perpendicular. Yes? An alternative mass transfer analog of this is in image 2 and 3 in the same PDF. Those are liquid crystals. Liquid crystals, you might have heard of LCD, liquid crystal display. There are different kinds of liquid crystals through which diffusion in one direction will be easier versus the other direction because you have the structured media. So meaning, and it's very likely that if you're working in some sort of complex transport phenomena, you might encounter non-isotropic or anisotropic systems.